la chance de rencontrer le professeur Mongi Bawendi et on s'est mis mutuellement à l'aise pour lever le maximum d'émotions, n'est-ce pas, professeur Mongi? Donc on s'est vu depuis ce matin et je me permets devant cette grande assistance adresser d'abord à monsieur le président de l'université de Sousse, à Madame Amel Ben Salah, représentante du ministère des Affaires étrangères, à Messieurs et Madame les vice-recteurs, à Monsieur le directeur régional de la santé, Professeur Chokri Hamouda, qui est le président directeur général de l'INEAS Santé, donc l'agence d'accréditation santé, Monsieur le président du CROM, s'il faut être, mes chers amis, messieurs, mesdames, les directeurs d'établissements et doyens, en exercice ou ex, je salue très fort, à Madame la présidente de l'amicale, en sa statut de présidente, pourtant elle fait partie, elle pilote le comité d'organisation, à messieurs les directeurs généraux des CHU de Sousse, au président de l'association médicale de Kérouan, à tous mes collègues enseignants, médecins, chercheurs, dans tous les domaines académiques, et à nos très chers étudiants internes, pour parler le jargon tunisien du statut en médecine en Tunisie, résidents, honorables invités. Je voudrais exprimer l'immense joie et le plaisir avec une profonde admiration aujourd'hui, à l'occasion du 50e anniversaire de la faculté de médecine de Sousse, de recevoir, de célébrer avec un géant de la science, un chimiste hors pair, celui qui détient le Prix Nobel de chimie 2023. C'est un véritable visionnaire, professeur Mongi Bawendi. Le professeur Mongi Bawendi n'est pas seulement un nom inscrit dans les annales de la chimie, dans l'histoire de la recherche, mais une source d'inspiration et un modèle à suivre pour tous ceux qui aspirent à exceller dans ce domaine fascinant et crucial. Sa carrière exemplaire, en ayant déjà de l'ADN tunisien, puis en transitant par la France, puis actuellement aux États-Unis, sa carrière exemplaire, riche en découvertes scientifiques majeures et en contributions inestimable à l'avancement de la recherche en chimie, avec tous les impacts, sa force, le respect et l'admiration. Ces travaux pionniers, même si c'est un domaine qui paraît hyper spécialisé, sur les nanomatériaux, ont révolutionné notre compréhension de leurs propriétés physiques et chimiques et ouvert la voie à des applications technologiques inédites qui ont transformé et qui vont transformer notre monde. Ces recherches ont eu un impact considérable dans différents domaines. Aujourd'hui, vous êtes dans une institution de santé, faculté de médecine. Donc, ces recherches ont un impact dans le domaine médical, l'électronique et l'énergie. C'est les domaines les plus, je ne peux pas dire importants, mais qui constituent un axe stratégique pour le développement de l'humanité. En médecine, les nanomatériaux développés par le professeur Bawendi ont permis de créer de nouveaux agents d'imagerie médicale d'une précision inégalée et de concevoir des systèmes d'administration ciblée de médicaments plus efficaces et moins toxiques et de développer de nouvelles thérapies personnalisées pour des maladies graves. Dans le domaine de l'électronique, les nanomatériaux du professeur Bawendi ont conduit à la fabrication de composants électroniques plus petits, plus rapides, plus puissants, ouvrant la voie à une nouvelle génération de dispositifs électroniques. Et en ce qui concerne l'énergie, les nanomatériaux du professeur Bawendi ont permis de développer des batteries plus performantes et des cellules solaires plus efficaces, contribuant ainsi à lutter contre le changement climatique et à la recherche de nouvelles sources d'énergie renouvelables. Au-delà de ces réalisations scientifiques remarquables, le professeur Bawendi est un homme d'une grande humilité, générosité. En tout cas, depuis la fin de la matinée, je crois qu'on l'a côtoyé de près, son côté sympathique, son côté modeste, son dévouement indéfectible à la transmission du savoir, son engagement profond envers l'enseignement et l'éducation et son souci constant de partager, en soulignant partager les connaissances avec les nouvelles générations, font de lui un exemple pour tous les chercheurs à travers le monde et aujourd'hui particulièrement en Tunisie. Cet événement, à travers la conférence qu'on a tous de découvrir ensemble, en présence d'éminents professeurs, chercheurs, étudiants et invités, tout à l'heure, nous profiterons de cet événement extraordinaire pour marquer d'une pierre blanche cet événement exceptionnel. Ce sera la remise du titre de docteur honoris causa au professeur Mongi. Bawendi. En lui conférant ce titre de docteur honoris causa, notre faculté de médecine ne fait qu'exprimer sa profonde reconnaissance pour l'immense contribution du professeur Bawendi à l'avancement de la chimie et à la formation de générations de chimistes talentueux. C'est également une occasion pour nous réaffirmer notre engagement vers les valeurs fondamentales de la science, la curiosité, la rigueur intellectuelle et la recherche incessante du progrès. Professeur Bawendi, encore une fois, d'abord c'était un plaisir de partager des moments en présence du conseil scientifique de la fac. Donc en mon nom personnel, au nom de la faculté de médecine de Sousse, du conseil scientifique, de tout le personnel, au nom de l'université, de tous nos invités qui sont venus aujourd'hui applaudir très fort votre présence et écouter avec beaucoup d'intérêt les conclusions de vos travaux à travers la conférence Avenir de la médecine tunisienne. Merci beaucoup. Merci à vous. elle va un peu... Je suis... donc là, on va être trop spontané, pas très officiel quand même. Quand on a invité professeur Bawendi, on avait donc le souci, je ne suis pas très fort en anglais, mais en tout cas j'allais me débrouiller quand même, mais on a eu recours à nos très chers étudiants qui sont très performants en anglais. Et donc, bien sûr, en rencontrant professeur Bawendi, il parlait très bien le français, à travers la petite période que vous avez passée en France, puis peut-être les allers-retours, vous maîtrisez, en tout cas en tant qu'enseignant, conforme à la pédagogie francophone. Bien sûr, votre speech sera peut-être en anglais, c'est clair. Donc notre chère étudiante va pouvoir, Massara, qui va pouvoir vous introduire pour la conférence. Donc vous restez un petit moment et vous prendrez place. Merci beaucoup.
Once again, on behalf of the students of the Faculty of Medicine of SUS, I welcome you. Dear professors, dear teachers, dear fellow students, and dear guests. The Nobel Prize, established by the will of Alfred Nobel, aims to recognize and honor individuals and organizations that have made significant contributions to humanity in fields of physics, chemistry, medicine, literature, peace, and economic sciences. Excellence, innovation, humanitarianism, internationalism, and ethical conduct are the main values of the Nobel Prize and are certainly values that are embodied by the Nobel Prize laureates across history, each in their very unique attempt to contribute to the betterment of humankind. Since 1901, there have been over 950 Nobel Prize laureates awarded across all categories, of whom only 185 awarded in the field of chemistry. And this day, we are happy, nay ecstatic, to have among us Professor Mongi Bawendi, the 2023 Nobel Prize laureate in chemistry. As many of you might already know, Professor Mongi Bawendi is a pioneering chemist renowned for his groundbreaking contributions to the field of nanomaterials. After completing his undergraduate studies, he pursued his doctoral studies in the University of Chicago. He delved into the synthesis and characterization of novel nanomaterials. Following his PhD, he then joined the faculty at MIT, where he established himself as a leading figure in the design of quantum dots. His work has revolutionized the field by providing efficient and environmentally friendly solutions for various industrial applications. And in recognition of his outstanding work, he was awarded, alongside his team, the Nobel Prize in Chemistry in 2021. His research continues to shape the future of catalysis and material science worldwide. His deep commitment to education, as well as his effort in mentoring students, never cease to amaze, and his accomplishment will always be an inspiration to generations of young scientists to stay curious while pursuing careers in science and technology. Before we jump into the conference, I would like to draw your attention once again to the QR code we put at your disposal to submit your questions during the conference and the brief interview afterwards. Without any further wait, ladies and gentlemen, please join me in welcoming Professor Mongi Bawendi.
Bon, je suis très heureux d'être ici à SUS et à l'école de médecine. quand j'ai commencé ma carrière en étant étudiant à l'université pour mon doctorat, j'étais d'abord un théoricien en mécanique statistique. Et ensuite, je suis devenu quelqu'un qui étudiait la spectroscopie, donc très loin de la médecine. Et quand j'étais, fait mon postdoc à Bell Labs, c'est là que j'ai commencé à étudier les nanomaterials. Et c'est vers l'année 2000, je crois, enfin, vers l'année 1996, j'ai commencé à penser aux applications biologiques. Et dans les années 2000, j'ai rencontré un docteur, quelqu'un qui était étudié le cancer. Et on a parlé ensemble, on a commencé une collaboration et j'ai appris beaucoup de médecine à cause de ça. Et en 2008, j'ai fondé une petite compagnie pour aider les chirurgiens à être plus efficaces à enlever les cellules de cancer. On a eu FDA approval juste il y a 2 mois. Donc j'espère que c'est une technologie qui va aider beaucoup de gens. Bon, c'est un voyage donc qui touche beaucoup de disciplines, mais elle touche la discipline de médecine aussi. Mais ce que je vais raconter aujourd'hui, c'est l'histoire du Prix Nobel, et aussi je vais toucher un peu sur les sujets qu'on touche avec les applications. Et malheureusement, l'anglais est la langue de la science maintenant. For better or for worse, you know, that's what the world uses to write and to communicate science. And so I will be giving the technical part of my talk in English because mon français scientifique est absolument nul. Okay, so what is a quantum dot? A quantum dot, je vais commencer par le début. What is a quantum dot? The quantum dot is a small particle, nanometer-sized particle of a semiconductor. You know of semiconductor because you know silicon. Silicon is what makes the computers work. But there are many kinds of semiconductors, and the kinds that we tend to use are called binary semiconductors. They're made of 2 different kinds of atoms, and the one that we've studied the most is made of cadmium and selenium, but there are many, many other kinds, and the kinds that are in applications actually don't contain cadmium because that's a toxic element. They contain elements that are greener, like indium or phosphorus. So if you're very good at making the material, like we became good at it, you know, they come out all the same size, and then you can really study them. Before that, you know, you had some ideas, but you couldn't really study the physics. And so really, the field started with physics. And so I have to tell you a little bit about physics to understand why this material is special. I love physics. I mean, every time I learn something new about a new field, you know, I find it very magical and beautiful. And the part of physics that I particularly like is called quantum physics, the quantum effects that you see at very small scales. And when you work at the nanoscale, quantum effects become very important. They become dominant. And so when you think about our scale, the human scale, and you think about an electron, you think of an electron as a particle that carries energy, it carries charge. And you can follow it in time, and you know where it is exactly. But if you take that particle, that electron, and you stuff it into a really tiny box, you can no longer describe it as a little thing that goes in a wire. It occupies the entire box at once, and the properties are no longer the properties of a little particle, they become the properties of a wave. The reason for that is something that you may have heard of called the Heisenberg uncertainty principle, or the basics of quantum mechanics. The Heisenberg uncertainty principle tells you that you cannot know at the same time the position and the velocity of an object when it's very, very small. And so we know that in the box, But that's all we know. We don't know where it is in the box. It's in the box. And that's the best we can do, right? And so that's why the properties really are dominated by quantum mechanics. So it's a wave in the box, and our box are these quantum dots. And we call that quantum confinement. It's confined in that box. And you know about confinement of waves, you know about sound waves can be confined in cavities. You know that a sound wave that's confined in a flute sounds different than a sound wave that's confined in a piccolo. The sound wave in a flute has a lower pitch than the sound wave in a piccolo. So the size of the cavity affects the pitch for sound waves. And you know that even more if you look at organs, right? You have small organ pipes and you've got big organ pipes, and you know the small ones are much higher pitch than the big ones. So it's the same thing when you have an electron wave in a box. If the box is small, then that electron wave will have the equivalent of pitch, and that is energy. It will have an energy which is higher than the energy of an electron in a big box, okay, like pitch, right? And so when I look at the different size particles and I put my electron in there somehow, well, first of all, how do I put the electron in there? Well, it's already full of electrons because it's full of atoms, and atoms have a lot of electrons. We've got to liberate one of these electrons to make it fill the box. And how do we do that? We shine light. We shine light, like blue light, right? And that blue light, which takes energy, then liberates one of the electrons in all these atoms and lets it occupy the entire box to be confined in that box. So we use light, we give it energy to liberate an electron so it can be in the box. And the small particles have higher energy, that electron is higher energy, and for the big particles, the electron is lower energy. Eventually, that electron is going to want to go back to where it came from. It's going to want to go back to fill the hole that it left behind. And it releases energy when it does that. And it releases energy in the form of light. So light is also a wave. So the small wavelength electron releases light that is a smaller wavelength. The large wavelength electron releases light that's a longer wavelength. And if you look at colors, on the blue side are small wavelengths, 400 nanometers, 500 nanometers, and when you get to the longer wavelength, 600 nanometers, 700 nanometers, that's red light, right? And so if you look then at vials of quantum dots where we shine blue light on them, in this case ultraviolet light, create that electron to fill the box and let it relax down or let it come back to where it was, we can see the light that's being emitted, that's called fluorescence, and the shorter wavelength light to the green, and the longer. And so that's the magic of quantum mechanics. Like you can just see with your eyes, right? The Heisenberg uncertainty principle, the wave functions, if you've heard of those things, you can just see it with your eyes. It's kind of magical. Okay, so October 4th, 2023, at 5:15 in the morning, I received a telephone call. I was fast asleep. My wife is asleep. And the phone rings, and wake up, I pick it up, and my wife wakes up and says, "What's going on? What's going on?" Because when the phone rings at 5:15 in the morning, it's maybe not something very good, right? And so you get very, very anxious. She gets very anxious. So I pick up the phone, and this voice says, "Is this Professor Bawendi?" But it has a Swedish accent. And so as soon as I hear the Swedish accent, and it's 5:15 in the morning, and it's the morning of the Chemistry Nobel Prize, I knew that it was from Sweden. So I turned to her and I said, "It's Stockholm." And she immediately knew what I was talking about. So she started screaming. One of our daughters came in and said, "What's going on?" And said, "He just won the Nobel Prize in chemistry." And then they said, "Please don't tell anybody for half an hour because we'll have the official announcement." And she was already texting, her brother and her friends. And I said, oh no, you can't text anybody, you have to wait until the official announcement. So then I went to take a shower, and I was looking at my phone, and I got a text from a former student in Korea congratulating me. And so I told her, how does he know? It's not announced yet. How does he know? Then I got another text from a student in Switzerland congratulating me. And what's going on? It turned out there was a leak, an accidental leak, so everybody knew except for me, because I was asleep. So the other two members of the trio were Louis Bruce. So I worked for him as a postdoc. After I got my PhD, I went to Bell Labs and I worked with Louis Bruce. And Alexei Ekimov was working in Leningrad in the Soviet Union at the time when he discovered what gave him the Nobel Prize. So they both were for the discovery of the effect that I just described, this wave getting small and large, rise to different colors. Alexei was interested in the color of stained glass windows. You know, in churches you have all these beautiful colors, and it was known that the red color was due to small gold particles. When you have a nanoparticle of gold, it actually looks red, and that was known already by Faraday. You know, in the late 1700s, he already had discovered that. What about all the other colors? So that's what he was interested in. And I looked at the recipes of the ancient recipes and realized that there were just a couple elements, a couple kinds of atoms in there that seemed to be the ones that would be causing the color. So he got rid of everything from the recipes except for what he thought was important. And then when he was heating the glass up at different temperatures, he found different colors, even though the number of elements was very, very small. And he realized that it was due to this quantum effect. And he wrote a paper called a quantum size effect, the first three words, in the Soviet literature at the time. The US and the Soviets, well, they weren't really talking to each other, you know, in 1980. Even less than today, and they don't talk to each other very much today either. But that was even less than today. So the Soviet literature was not, we didn't know anything about it in the West. Louis Bruce was working at Bell Labs, and he was interested in measuring how fast an electron would go from a semiconductor to a solution that contains molecule where you can do chemistry to create hydrogen. This was at a time where we had an energy crisis in the US. And in order to have more of these electrons go from the semiconductor to the liquid, you want to increase the surface to volume area. More surface you have, the more you can have electrons go to the liquid. So he made his semiconductors smaller and smaller and smaller until they became nanometer size. And he realized, or he saw, that if he made his sample in the evening and he came back the next day, it would have changed colors. And so he was very puzzled, you know, why is this happening? And by looking at images in the electron microscope, like the image I showed you earlier, he realized there was a correlation between the color that he was seeing and the size. And he realized that it was due to the same kind of physics. And he wrote a paper also called quantum size effect, you know, one in the Soviet Union, one in the USA, but the first three words are the same words. And kind of amazing, right? They didn't know anything about each other. Where do I come in? I come in because I was a postdoc with Louis Bruce between 88 and 90. I had made some progress in creating better particles, but during those 10 years, the quality was just good enough to see that there was this effect. But it wasn't good enough to do anything more. You couldn't study the details of the physics, and you couldn't apply them to anything. They were full of defects. In fact, I found, this is the paper that we wrote in '93, I found my old transparencies, you know, my handwritten notes, basically, that I used to give talks about, that date from 1990, that showed how they made the particles. And they made the particles in little water bubbles surrounded by soap in an oil, right? And so you have little tiny puddles of water, and then you add the elements as ions, and then you cadmium first and the selenium, and you create this little cadmium selenide at room temperature in water. So room temperature means the crystal doesn't really form very well. It's full of defects. It's a very defective particle. The surface, as I've shown, is it's kind of funny looking. And then they were able to replace the surface with organic, basically another kind of oil, so that they could take those particles and redisperse them. What I realized when I was at Bell Labs, and I could take these and use them as seeds, as little tiny seeds to grow further on top of them. And I grew further on top of them these molecules that are called phosphines at a higher temperature now, around 180 degrees or so Celsius. And I sort of stumbled by accident. And research is full of accidents, right? And you come across, you find something that's unexpected, and you can either discard it because it's not what you expected, can figure out why and change your direction and use it. So I found by accident that this particular molecule changed the color of my solutions and made it nice and beautiful. And I ran with that, and I did a lot of physics. But I could only make one size. And what I really wanted to understand was how materials change when you go from one atom to, say, 1,000 atoms. You know, one atom we understand at the atomic level, 1,000 or more than 1,000 atoms, you know, like 1,000,000 atoms. 1,000,000 atoms is like a piece of bulk, you know, the electrons are little particles that move around. But what happens in the middle? You know, the atom looks nothing like the piece of material like it's in your computer. And if I only have one size, I can't study the evolution from the atom to the big size. I needed more than one size. So then I went to MIT, and I told the faculty at MIT who gave me the job, I'm going to make many sizes of perfect particles, all the same size, and I'm going to understand the physics. And so they gave me a job. So I started at MIT, and then I tried to make that one size, because, you know, maybe I can make more size. And so my students, my first students, Chris Murray and David Norris, in the 1990s, you know, they were just a few years younger than me. You know, I was, 26 at the time, and they were 21 or 22. We tried to reproduce what I had done at Bell Labs, to make that one beautiful size, and it didn't work. We could not reproduce it. You know, I started at MIT in July of 1990. Chris started working with me in September of 1990. He was brand new. He didn't know anything about the kind of currents we were doing or how to analyze things. And David was going to do physics. He wasn't a chemist at all. Well, I really wasn't a chemist either, because I was a theorist first and a spectroscopist. And, it was very frustrating. Through those first 6 months, I didn't know whether I was going to get to keep my job, right? Because I couldn't do what I said I was going to do. But we realized that what I had done at Bell Labs was not that complicated. I had created little tiny seeds in one way, and then put them in a different solvent at higher temperature, and then let them grow, right? It's kind of like, it's called nucleation and growth. If you want to make a crystal, you know, if you have an image of an, usually when I teach my classes and for young students, I talk about the old German chemist, you know, from the 1920s and 1930s, trying to make a new molecule with his students and try to crystallize it so they can know what molecule it is. And the students trying really hard to get the molecule to crystallize, right? And it just won't crystallize. And this old German chemist that smokes cigars and has a beard, he goes over the vial and he goes, And this action and putting his breath puts all these little particles of dust and things from his beard and from his breath into the solution, and they act as nuclei to crystallize the new molecule. and then suddenly it crystallizes. So we needed to make little seeds to crystallize them so that we can have the growth. And so this is what we invented. We invented something that we call now the hot injection synthesis, which is that we very quickly introduce the metal, the elements that make up the crystal, into a very hot solution here at 380 degrees Celsius. Very quickly injected. That's the German chemist sort of rubbing his beard. At room temperature, they're stable. At high temperature, they're not stable. So they react with each other and form little tiny seeds. And then we let them grow over a long period of time. And then we also, because we were chemists, we invented a way to purify this. When you make a new molecule, you also want to purify it so you can analyze it. So we invented a way to purify the particles. And I have a video. Let's see if it's going to work. No, let's go straight to the video. Oh, we wrote a paper. We wrote a paper before I show the video. And I want to show two things on this. The abstract of the paper says two things that are important. It's simple, and it's a single reaction. And this turns out to be really important for applications, because if you want to manufacture something, you want to scale it up beyond a little pot in the lab to making a ton of this. It can't cost very much, right? It has to be cheap enough. And the cost of making anything is proportional to the number of steps to make it. This is true for chemicals, it's true for drugs, it's true for electronics. The more steps for chips, the more steps you take, every step costs money. For one step is the least expensive. So that was really important. And I didn't realize that at the time, how important that was going to be. So let me just cut to the chase here. I just want to show you this. These are spectra. So this is blue on the side here and red on the side here, and the peaks are where the thing absorbs light. And you see it march along across the visible from blue all the way to red in very tiny steps. And that's the ability that we had, that Chris had, my first student, to really get the particles to be all the same size. Okay? And many, many sizes now. 2 nanometers to 15 nanometers. So I had a size series, exquisite control over the size, so I could start studying the physics and the applications. Okay, so let's see if the video is going to work. Here we go, yes, the video. So it's just like the cartoon. He's got a syringe. There's the pot here at 350 degrees Celsius. He quickly injects, creates the seeds, quick change of color. Those are the seeds. They're about 2 nanometers in size. Then there's slow growth. You could take a coffee break for a while if you wanted to, but no, I'm going to skip here 20 minutes and show you what happens. Okay, 20 minutes later, now it's much darker because they're much bigger. So that's the change in larger size with the wave of the electron being bigger, going further and further to lower energy. And you see the different colors as he takes the solution out, as it grows, then you can see the change in color as the little particles become bigger and bigger. So you see from small particle here to, then you shine UV light and you can see the light being emitted, the fluorescence from the particles from green to red. Okay? So that synthesis, which looks really simple, is why I won the Nobel Prize. But it's not just that simple, okay? Because if this was useless, they wouldn't give a Nobel Prize for this, Because the Nobel Prize in chemistry, the average time between a discovery and the Nobel Prize is 30 years. Okay, so this was in 1993, and I won the Nobel Prize in 2023. That's 30 years. Because they need to wait until to see how important is this. Important for science or important for the applications that come later. If the nanoparticles were completely unimportant, then this would not have any impact, right? There would be no impact. But it turned out to be so more important than just a fun little thing here. We did some fundamental science because initially our curiosity was what happens in the size range. It was the fundamental curiosity of materials. It wasn't the applications. In 1993, we had no idea what these things were good for. And we didn't really care. We didn't care because we were just motivated by the science, by the curiosity of a new material that we were just discovering. And so in this case here, you can see, just go very quickly, this is at 4 Kelvin, almost as low temperature as you can get. This axis is basically size, so these are large and these are small. And these are effectively, if you know music, you know that you have the fundamental and you have the harmonics, right? The harmonics are at higher pitch. So these are, what you see here are the energies or the harmonics of the electron. And there's something funny going on right here. These harmonics, the blue and the green, they don't go monotonically. They try to cross each other. And in physics, when you see that, it's called an avoided crossing, and it gives you fundamental information about the way that electron interacts with all the atoms inside the box. So these are the kinds of really subtle problems, only people in a very small community, very small chemistry and physics community would be interested in this. I was really interested in this. This is why I made the particles. That's my fundamental science driving my curiosity. So over the years, we did a lot of this kind of work, which has impact in a small field. We also found that the particles, because they're all the same size, they want to crystallize. And if you think as each particle now being a kind of an artificial atom, what we're making here are new solids with a new kind of atom, right? And maybe these new solids have new properties. And this was, and they can be made fairly large. So now we can really study these new properties. And now this was done by one of my first students also, Sherry Kagan. There's a 23-year-old Sherry Kagan here now from 30 years ago. And now she's a professor at the University of Pennsylvania. And she's married to Chris Murray, the other first student. And now there are thousands of people in the world that study these sorts of arrangements to see if they can make these into new conductors for electronics, for instance, using the nanoparticles as the effective atoms, creating a new periodic table to create new material. It turns out that the process we made isn't unique to semiconductors. It can also be applied to magnetic materials. And once you start creating multiple materials, you start to combine them. And you think, can I make something that has multiple properties at once? And so in this case here, we combine these small particles of semiconductor, these quantum dots that emit light, with very small particles of magnetic materials. These are iron oxide particles, little tiny magnets, nanometer-sized magnets. Combine them together and we make bigger particles, but they're also all the same size. And they're made up of many particles of each one of these. And they're both magnetic. If you put a magnet, the solution goes through the magnet, and they also emit light. The reason why I wanted to study them was because I had learned about medicine, and I had been interested in creating something that was both fluorescent and magnetic. Why? Because something that you can see in tissue at very high resolution, optical resolution, and something you can also use to increase contrast in MRI. So you need something magnetic to increase the contrast. Then you can go in and look at high resolution optically. And we applied these with colleagues at the medical school on brain tumors. These are mouse models of glioblastoma, where using the magnetic particles, we can enhance the signal. And then we can go in. These mouse have a window model, so there's a window that covers, the skull is replaced partly by a window, so we can go in with light, and then at high resolution we can see then the structure of the blood vessels, and look at how misshapen it is, etc. And I worked with this group at Massachusetts General Hospital, part of Harvard Medical School, for many, many years, closely collaborating them to understand the microenvironment in tumors. This was one of the things we did. So when you have something that's very bright, very efficient in emitting light, and that this is the absorption, all of them can be excited with one wavelength, around 460 nanometers. That turns out to be the wavelength of a new kind of light material that was called gallium nitride diode that was discovered in the 1990s by a Japanese guy named Nakamura, which we use for lighting today. It's a blue light-emitting diode. All the LED lamps that are replacing incandescent and fluorescent all over the world are many, many times more efficient, and they're all based on blue light. And so if you have a good source of blue light, you can think of all sorts of things, because you can use the blue, efficient blue light then to create all of these colors. Okay? You can think of this as your engine, and then the output can be anything you want. Okay? So combining these new, so this is being curious about what everything else is happening around you, right? It was recognizing that there's this new source of blue light that could be really, really important, and how can we use it, right? How can we use it? And that gave rise to the first application. The first application was in cell imaging. Company was started called Quantum Dot Corporation, and we used it to image cells, and it's still a product that's sold by Thermo Fisher that biologists or cell people that want to image cells buy. Started in 1998. So I want to go back to the timeline, right? 1980 was the discovery of the effect. 13 years went by where not very much happened. 1993 was making the material. By 1998, there was the first commercial application. So 5 years later, so making the material was really kind of important, right? And then the application started very, very quickly after we were able to make the material. We devised, then later we went beyond cells, we went into tissue. Again, this is a mouse model. We engineered the particles with organic groups so that they would be benign to the tissue, so they wouldn't stick to the tissue, using PEG groups at the outside. And then we looked at to make sure that they would extravasate, they would get out of the blood vessels into tissue properly. And then you can target, you can put antibodies or other proteins on the particles to do targeting. This is now an experiment we did where we had 2 different colors of quantum dots with different kinds of antibodies to target a stem cell in the bone marrow to try to understand what the environment around the stem cell was. There was a controversy whether the environment was oxygenated or not oxygenated. But in order to understand that environment, you have to find the stem cell first before you can study it. And so finding the stem cell in vivo without affecting it turned out was a challenge. But with the quantum dots, we were able to do that. We were able to inject 2 different kinds of quantum dots in the mouse, and then go with a microscope, a confocal high-resolution microscope, and see. So when you have red and green together, that gives blue. That gives yellow. Yeah, red and green. You mix those 2 together in fluorescence. That's yellow. And there's one of those cells. And now we can try to study it in its running way. The other cells are just regular cells and not stem cells. So these are very rare cells, and we were able to find them. That's a hard experiment. But, and then we realized, these quantum dots can do something that other organic dyes that are used can't really do well, which is to go even beyond the visible light into the infrared, colors that we can't see. Why is that interesting? It's because when you look at tissue scatters visible light very well. That's why, we're not transparent, right? The skin scatters light. But if you go to longer wavelength light, the penetration is much, much longer, okay? Visible light stops around, let's say, 700 nanometers. If you go double that to 1.4 micron, 1,400 nanometers, the light can go much, much deeper. And so we created these composite particles, let me go back here, these composite particles that emit in the infrared and injected them in this mouse model again. So this is another glioblastoma mouse model, and the colors are all fluorescence from quantum dots. The red is the veins, the blue is the red is the arteries, the blue is the vein, and the green is the tumor vasculature. And then when we have the structure defined by the fluorescence of the dots, we can go in and inject these infrared emitting particles and then look at the blood flow in the different areas. And then we can concentrate on the healthy tissue in the brain or the cancerous tissue. You can already see that the structure of the healthy tissue is more organized than that of the unhealthy tissue. It's, this is more of a mess. This is more like spaghetti. And this is more, plumbing, regular plumbing in your house. So when you look at the dynamics, so this is the cancer tissue, this is the healthy tissue, and you see these very bright little spots. Those are these particles that are floating around. They tell you how fast the blood is flowing. And you can see in the healthy tissue, they're all flowing pretty fast. Especially in the big vessels, you can't even see anything because they're flowing so fast. And now you look at the cancerous tissue, and you see, well, that blood flow here, that's not going anywhere, right? Doesn't look at all like this. And this is why the tumor environment becomes acidic, why the byproducts of biology stay there. You have acidic, you don't have any, you can't get oxygen in there, it's apoxic, right? It's not at all a healthy environment because the blood flow doesn't allow nutrients to go to the tissue. And so that's an environment that's very good for the cancer cells. They become very aggressive in that environment. And so our collaborators at the medical school were interested in creating therapeutics that would change the blood flow from this to that. Why do they want to do that? It's because there are all these drugs out there that could be really great drugs for cancer, but if you can't get them to the tumor, that's useless. So the first thing is to try to get the blood to go into the tumor, so when you administer therapeutics, it actually gets to where you want it to go. And they found some things, that would accelerate the blood flow and that would make it more like that. I wrote some papers on that. Let me tell you about the application that actually is a very large-scale application. It's not in biology, even though biology was the first one, and it's kind of funny because the biology was the first one, but it was also the hardest one. And I think that's because we were chemists. And the first thing we thought about was small molecules and antibodies and proteins and everything that was of that same size scale, and our friends were biologists. But then I met an electrical engineer in the early 2000s who was working on new kinds of displays. And he thought, wow, I love these colors, they're so bright and beautiful, I want to use them for displays. And I said, yeah, but don't you already have something called organic light emitting diodes, OLEDs, that work pretty well? OLEDs are the kind of displays that you find in your iPhones, if you have an iPhone, or in some of the televisions. And he said, no, this could be even better than OLED. So I said, okay. And the first thing I did, I actually did this myself, is I incorporated the quantum dots in polymer in little tubes to show that we could stabilize them in polymer and shine blue light on them and see the emission coming out. And we started a company together. We started a couple companies, actually. The first company was Nanosys in 2002 that I started with people from Berkeley, and QD Vision in 2005 with my MIT colleagues. And the first product that came out based on this idea of absorbing blue light, re-emitting of different colors, but not for biology, but for really simple things like creating colors in displays or lighting, was these light bulbs. So what are these light bulbs? This was the beginning of what we call LED light bulbs. You know, these new light bulbs that don't take much energy. And in 2010, when they first appeared, they were really expensive. They were $100 a piece. Nobody could afford them, except maybe, you know, big universities like MIT. And the color didn't have enough red in them. So the color was very blue. We called it the color temperature. The color temperature was very high. And so we thought, okay, we can warm up the color. We can put more red in the color by taking some blue light and shifting it to the red. If the color is too blue, then if you have it in your bathroom and you look at yourself in the mirror, you think that, you know, you're very sick. You look all gray, like you're dead, right? Because your blood is red and it doesn't reflect the light. If there's no red light, it's just not there. So this makes it appealing. Humans like to have a lot of red in their lighting. That's why we like the sunset, you know, when it's cold in some place where we like to make a fire, a red fire. We find that very warm and soothing. So making the light more red was really a great idea. And so you could buy these things. But then very quickly the price changed from $100 a piece to $20 a piece. And then you couldn't make any money with the quantum dots because, you know, the company that makes the quantum dots, it needs to make money too. And if the thing is $10, maybe you can add 50 cents, you know, half a dollar, and that's not enough money to make a business. So that company, QD Vision, you know, they were going to go bankrupt, and they thought, well, that same principle could be used in televisions. Okay? And so how would that work? How does that work? Well, again, you have these blue, very efficient sources of light. You put in plastic the red and green emitting dots, and you take some of that blue light and you make it into green and red. Then you have blue, green, red, RGB, and with that, you make all the colors that the humans can see, right? You just need RGB. This is a very efficient way of making all the colors that you can see. Much more efficient than the previous generation of televisions. And Sony was the first company to make these things, and they were sold in 2012. And when they came out, I asked them to send me a television, because after all, I had invented the technology in there, right? And they said, no, you have to buy it. I don't want to buy it. You know, it's not right. So I asked QD Vision, the company that made the quantum dots, and I said, can you give me a television? And he said, we don't have any. We asked Sony, and they won't give us any. So I ended up buying one, you know, on the web, and it took 4 tries for this television to come back without a cracked screen. It was a big 65-inch television, you know, huge television, and Sony didn't know how to package it. So every time they shipped it, something would bang on the screen and it would break. So maybe that's why Sony stopped making them, I don't know. But Sony only made them for 1 year. But Samsung, another big company, decided this was a great idea, and they bought QD Vision in 2016. And the reason why they bought QD Vision wasn't because of the technology, really, because if you know big companies, you know, they just use things, you know, they tend not to, well, anyway. The reason why they bought it is because QD Vision had trademarked the term QLED. Q, if you get rid of this little bar here, it becomes OLED, which was the technology, organic light emitting diodes, that its competitor, LG, the other big Korean manufacturer of television, was using, right? And so Sony could say, we have QLED, LG has OLED, we have quantum in our TVs, right? Q is quantum. It's marketing, right? It turns out it's a pretty good technology, but it's also great for marketing. So ever since 2015, Samsung and now many Chinese companies and companies all over the world use quantum dots to create the colors in their TVs. In fact, the latest television from Samsung uses both OLEDs and quantum dots. The way it works is that they make little pixels of blue light, now using organic molecules, and then they print on some of them red and green emitting dots. So it's not based on these blue diodes anymore. Each pixel of color in the TV is individually addressed, so you can turn them off if you want black, turn them on if you want a different color, and so you get more energy efficiency and better color, etc. And that's the new technologies of all. And I went to a place called, in California called Society for Information Display, where all these big companies present their new models of displays for laptops, for TVs, for watches, for AR, VR displays. And the amount of companies that are using quantum dots to create better displays, to me, was, I didn't expect that. I mean, it was unbelievable. Unbelievable to think that, in '93, when we made this synthesis, we had no idea where we would go, and that 30 years later, these things are made, and I went to visit a factory where they make the dots in large quantity. These are huge. It's not my little flask anymore. They're 5,000-liter tanks where they make the dots. It's huge. And they make them continuously, and they ship tons of this thing to all these display companies. Just amazing. There are other applications, photovoltaics, and the next kind of application that they're all working on, which we worked on also early on, was instead of using blue light to generate the dots, to excite the dots, what if you just use electricity directly? That means current in, light out. And then we don't have to work with OLEDs anymore. So this is the new generation that we hope is going to come out in about 5 years. Okay, so it keeps going technology. We worked on photovoltaics. This is me wearing sunglasses that are coated with quantum dots that also generate electricity. Kind of fun. There are companies that are commercializing night vision with quantum dots, much less expensive than the technology that we have today, and I think that's going to catch on. Okay, that's the end of my presentation, but my technical presentation, but I want to say where we are today, okay? Where we are is that semiconductors is where we started with the quantum dots, but the same sort of technology at the nanoscale to create materials with exquisite control is also applicable to metals and magnetic materials, and then we can make the dots of all different kinds of shapes as a community. Now there are thousands and thousands of groups all over the world that work on this, and their output is incredibly creative, much better than I could ever have imagined, And we can combine them into new materials, new assemblies. The real applications, like in displays that are sold all over the world, biomedical imaging, light sensing, little sensors of light and solar energy, and the common applications in catalysis and electronics, optics and quantum systems. So the future is much brighter than I ever thought it would be. In 2000, I remember both in 2000 and 2010, we talked to other people working in the same field, or the old generation, because by then I was the old generation. And we said, when is this going to stop? We've done everything. When is it going to stop? Why are people still going in this field? What are they going to find that's new? And, 20 years later, it's still growing, and we're still discovering new things, because it was really at the frontier of a new material. I've had a lot of students over the years. I've had about 150 people work in my lab, and they're the people that really did all the hard work. They're the important people, right? I'm just a manager. I tell them my ideas, but they're the ones who implement them. And a few weeks ago, we had a reunion, and about 100 of them came to celebrate with me, the field, and we had a great time. This guy here, heading the 2C, he was one of my first postdocs. He's Tunisian, from the south of Tunisia. And then my 5 things, right, which you all know about. Okay. Thank you. je m'assois. Merci.
En biologie, les résidents en médecine, mais je Prix, et ils vont vous poser quelques questions.
D'accord.
Dear guests, as soon as we were informed about the conference of Professor Bawendi, we put at the disposal of our faculty students a form in which they can submit their questions. A load of questions was submitted, and we made a selection of few. We will be conducting a brief interview with Professor Bawendi. Majid and Dream will handle it, and then we will move to the Q&A. Thank you.
Thank you, Masara. Again, we are very delighted to have you among us, Professor Bawendi. And first, I want to ask you, is it your first time in Tunisia? And how is your stay going so far?
Well, it's not my first time in Tunisia at all, because I was, although I was born in Paris, I think before the age of 1, I came to Tunisia with my parents because my father was Tunisian. And he went back and forth between Paris and Tunisia for many, many years. And I went to elementary school in Tunis for a few years before going back to France. And then the last time I was in Tunisia was 2009, 15 years ago. Sounds like a long time, but when you're old like me, 15 years is like not that long ago. So everything, I remember a lot of things from 2000, and certainly from before that.
And how is your stay going so far now?
It's overwhelming. You know, how the interest in the work and in me, it's kind of overwhelming. But I'm very happy to be here.
So we're glad you're enjoying your time here, and we hope you get to experience Tunisia to the fullest. So now let's dive into more serious matters. We received many questions from our students about your career, and the most asked one is whether your current career as a chemist is a premeditated choice or it's the unexpected result of a series of circumstances.
It's the unexpected result of a series of I think, you know, life is a series of accidents in a way, of accidental choices. I had a really good teacher in high school, a really good chemistry teacher. I think if I'd had a really good physics teacher, I'd probably be a physicist. But he was a really good chemistry teacher. And then I was in the middle of the United States, something we call the Midwest. And I went to college at Harvard on the East Coast. And if you know something about the US, the coasts look down on the center of the country a little bit, you know. It's the coasts that are the elite part of the country in a way, although the Midwest wouldn't like to think of that. And I went to Harvard and I met students that were coming from private schools that were much more advanced than my school, high school. And I thought, you know, these people that are studying physics in college, they're much smarter than me. I would never be able to compete with them. And I liked chemistry, I was pretty good at it. And I had a good chemistry teacher as my first year at university also. So I said, okay, I'm just going to stay in chemistry because I like it. And these other kids, they're just too smart and too good. And I'm intimidated. So I stayed in chemistry. But I liked physics enough. And so I ended up being what's called a physical chemist, somebody that's at the intersection between chemistry and physics. And, you know, what I've done here is really at the intersection of the two.
So that's very interesting, Dr. Bawendi. As you were saying that you had a lot of mentors while you were growing up. If you can, like, say to us, what skills and values did they teach you?
Well, I'll tell you about my last mentor, which was Louis Bruce, who was a Nobel laureate. When I went to Bell Labs, you know, I discovered a new way of doing science. Bell Labs was incredibly special. It was an incredibly special place. It was extremely collaborative. People from all disciplines working together. And he really embodied that. He would go knock on people's doors that were in all sorts of disciplines and just ask questions and learn from them. And this way of breaking boundaries between disciplines and learning about other things, I tried to do that when I got to MIT. I think that was really important for my development.
So having such a mentor can be a great impact on you. The same thing can be said on your background. So how did your international background influence you?
So this is the question that I get asked a lot, and I've thought a lot about it over the years. And as I've said in one of my interviews, it's been the subject of a lot of therapy. You know, I grew up I was born in France, I grew up in there, but in Tunisia, and then I moved to the US, and I didn't know any English when I got to the US, first time when I was 10, and then I came back when I was 15 in the US. And every place I went, as my parents moved, it felt like a new place. And where we were in the US was a town called West Lafayette, but it's the home of a university called Purdue University, P-U-R-D-U-E. And, you know, when I was a kid and speaking French, you take that U and you replace it with an E, it becomes perdu. And I was completely lost. I was completely perdu when I arrived because I didn't know a word of English. I didn't think it would be necessary to learn English, but it turned out to be really important to survive. So I always felt like I was a little bit of a stranger everywhere I went. You know, even when I went into chemistry, when I did my work in synthesis, I wasn't a synthetic chemist. I didn't really know anything about how to make molecules. I was a physical chemist. I like to measure things, you know. I like the quantum part of things. But in fact, I remember when I started as a graduate student, I wanted to go somewhere where I didn't have to make anything. I just wanted to buy things from companies and study them. And then suddenly I had to make something and use a very specialized kind of chemistry called organometallic chemistry. I didn't know anything about that kind of chemistry, so I was an outsider of that field, right? And I think my background of being an outsider everywhere I went, but becoming comfortable being an outsider made me comfortable to accept and go forward with the kind of science that I did. You know, always on the outside. I didn't know anything about medicine, but hey, you know, I can learn it, right? Or electrical engineering or displays. It's all fascinating, and it's okay, you know? So I think the idea of being an outsider was something that defined me from a very early age.
So we guess that everything somehow came together and led to where you are right now. A teacher, a scientist, and recently a Nobel Prize winner. So actually we want to know, we're curious to know, what do you enjoy the most, doing research or teaching students?
Oh, you know, to ask me what I like the most is a very difficult question. It's kind of like asking, you know, which is your favorite kid, you know? I love teaching. I love teaching students, the undergraduates, but also the graduate students, I taught freshman chemistry, the first year chemistry for many, many years. And that's a different, you know, when you teach first year chemistry, it's a performance. You have a big classroom, the material is not very hard, but you have to keep their attention. You have to perform, right? You go to first year graduate school, the material is much harder. It's much more interesting, really. And so you're much more intellectually stimulated by the material. And then your students that work with you, you're also teaching them, you know, in a different way. This is more like being your apprentices, right? They're your apprentices. So that's, you know, part of being an academic scientist is the part that I really, really like, is this interaction with the students and then creating research out of that.
Other than that, the majority of our students are thrilled to know how would a Nobel Prize winner spend their pastime?
Oh, how do I spend my pastime? Well, there's before October and there's after October. Before October, I really enjoyed sports, you know, but not team sports. I like to ski, I like to climb, I like to rock climb, I like to ice climb, I like to cycle, I used to like to run a lot, so anything that's very vigorous, where your mind can take, you know, can be removed from your everyday life and be out in nature. After, well, let's just say that I've been traveling a lot. I'm on the road once a week almost to different places in the world, and I hope that it quiets down, because I miss nature and cycling and climbing, and I want to go back to it. And it's, you know, it's good for my health to go back to it too. So.
Certainly, Dr. Bawendi, winning the Nobel Prize is a lifetime achievement. So we cannot keep ourselves from wondering about the process that led to it, especially teamwork. So a lot of students here would love to know how to embody the values and quality of a leader, and how to manage the conflicts in a team, especially your team that's filled with brilliant scientists.
So conflict management is really hard, because you've got a team of, you know, maybe a dozen people that are all really smart, and, you know, it's normal for people to want to get credit for what they've done, right? And it's normal for people to be ambitious, and it's really hard to convince people to work together sometimes. To work together for the good of the progress, especially at the beginning. You know, they want to say, okay, but I want to do something that's for me, you know, but you need to convince people that each little piece is important. But I make sure that everybody in my group has a project that's their own, that they can collaborate with other people to help them, and that they help other people with their own projects. So I really try to instill teamwork in one way or another, and really reward teamwork. And I get very upset when people come and tell me, you know, they don't want to work with somebody because they want to have their own thing, right? And well, I don't show that I'm upset. You know, I get upset internally, and then I try to change their mind, you know, and convince them, you know, not by being upset, by trying to convince them in a logical way.
So leadership and teamwork are fundamentally important for the success of any project, but also is resilience. So while you're working in this project, did you or your team face any hurdles or difficulties?
So, in research and really any field of life, you're always faced with challenges. Challenges are part of the normal advancement of any career or especially in research. In research, you never know for sure whether things are going to work or not. And so usually when you try to do something for the first time, it usually doesn't work. And then you have to have perseverance to make it work. And, the last big problem that we had, challenge, was during COVID. So we had an experiment that was a very hard experiment that we'd spent 2 or 3 years putting together, and it was ready to go. And it was only going to take like 3 weeks to get the data that we needed. And it was ready to go, and it was March of 2020. And everything shut down. And it shut down for 3 months, and then we went back to the lab, and then all the equipment was broken. Because, like plumbing, if you don't use it, it starts to break. And things were not working, and you couldn't go in the lab. And it took us 2.5 years after we were back to get back to work. So we basically lost 2.5 years. And the challenge of that is to convince students, to keep going, because it's really easy to give up when you've spent 2 years to try to do something, and then it completely fails. To go back and spend another 2 years to fix it, to get back to where you were before, that's a really hard management problem.
So, Professor, facing these obstacles, did you ever think about giving up, and what kept you going?
I thought of giving up at the beginning when nothing was working. I don't know what kept me going, I felt like, I didn't have a choice. I just had to keep going, yeah.
And to which extent were you positive about winning the Nobel Prize?
Was I positive about winning the Nobel? Yes. Well, winning the Nobel Prize is a very positive thing, for sure. What it is really an affirmation. The Nobel Prize, for me, and Louis and Alexei, is really a Nobel Prize for the field, It's really a Nobel Prize for the thousands of people that now work in this field. And it's not just me that's being rewarded, it's actually the entire field, and they're all feeling like affirmation that what they're doing is worth it, that it's important. I think that, to me, that's the best part of the Nobel Prize, is all these people that are working in the area feeling, yes, this is important.
So Professor Bawendi, with technology and AI taking over, we received a lot of questions about your perspective. Are we going to witness the surge, and most importantly, the disappearance of a lot of jobs, especially in the scientific field?
The what?
The surge or the disappearance of jobs with AI and technology?
No, we're not going to see disappearance of jobs. I don't believe that at all. We're going to see different kinds of jobs. We are starting to use AI in my own research. It's a tool, right? It doesn't replace. It makes what we do more efficient. It's a tool, just like the computer is a tool. It's just, for instance, we use AI algorithms to speed up experiments from 10 hours to 20 minutes. That's an incredible. We use AI to search for new ways of doing things. It just makes things a lot more efficient, but it doesn't replace. I don't think it will for a long, long time. It doesn't replace the need for creative brains. AI is trained from the past. It can do some things in terms of explaining some things, but I think in predicting the future or creating really, really new things, I don't think AI is there anywhere close to that at this point. And it's, you know, it's still a very primitive tool. Even though it seems really amazing, like it's magic, it's still quite limited in terms of what it can do creatively, which is really what humans are really good at, is be creative.
So, Professor, now we want to get more into your vision of the future. And what role can science play in the prosperity of humanity and in the resolution of global issues?
Well, you know, science is international. The scientific community is all over the world. You know, we communicate with each other and we see each other, and I love to visit people in other countries, and I think that's science is one of these few things where the world is one place. And I think that's really important because we're all humans, you know, we all want the same things. We need to be able to communicate together without conflict, and science is one way that we are able to do that. You know, it's one model of being able to do that. And science advances humanity by providing better tools. You know, in medicine, you know, where we are today in medicine, think about where we are 100 years ago. We're much better off today with the kinds of medicine we have than 100 years ago. 100 years from now, it'll be amazing. So science and technology have not only a role to play in advancing human health and human wellness and our ability to interact with each other and the environment and all these things, and also our being able to enjoy life. It has a role to play, but it's not just has a role to play, it's critical to get there. And so I'm a very strong believer in science for the good of humanity. I think that's really important.
So certainly, in one way or another, science can play a huge part in the continuous betterment of humanity. And I think this can only happen by raising generations of scientists and researchers. So as a professor yourself, how to foster the passion of students for research worldwide, and especially in Tunisia?
Well, you know, part of having won a Nobel Prize, I feel like I have a responsibility now to go and talk to students like yourselves, and hopefully, you know, instill the idea that science can be incredibly rewarding. It's an incredibly rewarding career to be in science. And it's a very social career as well. You work with a lot of people, you meet a lot of people, and you do things that are really important for the goodness of the future in humanity. So, you know, by showing that, you know, it's possible to start with ideas and create things that didn't exist before, that are advancing knowledge in some ways, I think that's really my job now, part of my job.
And finally, Professor Bawendi, we would like to ask you, what piece of advice would you give to young scientists, young researchers, or even maybe to your younger set?
Well, I mean, I have my 5 things up there, right? Yeah, I mean, okay. But seriously, I mean, the thing that I tell we have the second year in graduate school, we have an exam, it's a proposal exam. And I can tell very quickly who's going to do well and who's not do well, you know, in their career, and who's going to struggle a little bit more by just asking simple questions. And the people that have been curious about not just the big picture problem, but also how their experiment works, how the tools that they use to do the experiments, how those work, and why does it work this way or that way. So just having an inherent curiosity about the world around us, that to me is much more important than being smart.
Thank you, Professor Bawendi. On behalf of all the students of the Faculty of Medicine of SUS, we would like to thank you for your kindness and pertinent answers.
Thank you again, Professor Bawendi, for your input. Well, we've received lots of questions.
Ok. Des questions, d'accord, d'accord.
Sorry for the struggle, people are curious. We received lots of questions that were submitted by the QR code, lots of which we discussed during our interview. Due to the limited time, we will be taking the first two questions. Umayma wants to ask you, Professor Bawendi, if you could provide more insights on the factors influencing the lifetime and stability of quantum dots, and how do quantum dots compare to other nanomaterials in terms of their effectiveness when integrated into sensors?
What's the last part?
How do quantum dots compare to other nanomaterials in terms of their effectiveness when integrated into sensors?
Okay, so we worked very hard, and this is a very technical, specialized question. Yeah, so we worked very hard to understand how to do chemistry to encapsulate the quantum dots so that they would be less prone to degradation from the environment. So we created structures that have the quantum dot in the middle, then have other inorganic materials around the outside. Those are called core shell structures. It's like an onion, you know, you have layers and layers that protect the center. And on the very outside, we have organic groups that do another level of protection. So we've been able to, as a field, engineer the material to make it more and more robust. And that took a lot of hard work, but you know, now they're robust enough that in a television set, for instance, they're going to last longer, you know, they could probably last 30 years or 40 years without changing.
Perfect. These following questions are about the medical applications of nanodots. Marwa wants to know if nanodots can be used in the early diagnosis of cancer, and Ahmad would like to know if quantum dots will potentially impact the medical imaging.
Okay.
If so, how?
Yes. So the quantum dots that we use, we use it only in animal models to understand the biology at this point, because I'm not comfortable putting these sorts of materials in humans without understanding exactly what happens to them. And if you want to do clinical trials to understand the toxicity, somebody's going to have to pay for it, and it's going to be really expensive. So I think that quantum dots in living humans is not going to happen for a very long time, and that's okay. What we've learned from the quantum dots in animal models, we've carried over to different kinds of nanomaterials. We've carried over to iron oxide particles for contrast in magnetic resonance imaging. And those, I'm quite comfortable, will become available in humans to replace gadolinium contrast agents. And we've learned about the biodistribution and biokinetics of these nano objects, and we've replicated that using molecules, molecules that are already approved to be used in humans. So they look like the quantum dots in almost every way, except they're not made out of these metal materials. They're made out of other materials. And those are approved now for humans.
Well, thank you very much, Professor Bawendi, for your enriching conference and interesting input. Ladies and gentlemen, while we wait for the honorification ceremony of Professor Bawendi, please remain seated and allow yourself to enjoy the soothing musical break presented to you by Raed, Fayrouz, and Ahmed.